Good, thank you very much. My name is Perry Brown. I'm the Provost and Vice President for Academic Affairs at the University of Montana, and I would like to welcome you to the 2013 beginning to the series of Provost Distinguished Lecturers. The distinguished lecturers are really people from the UM faculty, most of whom have won some kind of significant award or had a really significant accomplishment in terms of production or exhibition or something like that in the last year. And we like to honor those people by allowing them to, or having them provide a Missoula audience some indication of the kinds of things that they do, the kinds of things that interest them, and really what their career is all about, and probably why they won an award in the first place. And you will see that as you see these people talk to you. So this is the first of the series for fall of 2013. The second lecture that we will have will be on October 30th, and that's Jody Pavlock from the History Department, and she's going to be talking about politics of coal mining in Chile. And she has had a distinguished part of her career examining that set of issues. But anyway, let me just welcome you to this lecture this evening with Mark Kayll, and I'm going to ask Jenny McNulty, the Associate Dean in the College of Arts and Sciences, to introduce Mark to you.
Thank you, Provost Brown. In addition to being an Associate Dean, I'm also a professor in mathematics, so it's my great pleasure to introduce Mark Kayll tonight. I have known Mark for a long time, and sometimes when a speaker is introduced by a longtime friend, they try to embarrass them a little bit. I'm not going to do that, Mark. I'll just say some nice things, and see me later for more details. So Mark grew up in Vancouver, Canada. After completing a bachelor's degree at Simon Fraser University, he ventured down south to the US of A and Rutgers University, where he earned a doctorate in combinatorial mathematics. By the way, combinatorial comes from the word combination or combine. And as you'll learn tonight, that's just a fancy way to say counting. This fall marks the beginning of Professor Kayll's 20th year at UM. Not only has Mark had a long career at UM, but he's also had a very successful one. He has written many papers, had numerous co-authors, supervised student research, and taught a variety of classes, one of which I think we'll hear about tonight, involving math and music. But I do want to highlight two developments in Mark's career that just happened recently. One was in 2012, he received the Mathematical Association of America Carl B. Allendorfer Award for expository writing. His article was entitled, "Integrals don't have anything to do with discrete math, do they?" It appeared in the Math magazine, and it's a great article. Please check it out. More recently, the Simons Foundation, whose goal is to advance research in basic science and mathematics, recognized Dr. Kayll with a 5-year collaboration grant for productive scholarship. Without further ado, let's welcome Dr. Mark Kayll and learn more about 1, 2, 3.14.
Well, thank you, Jenny, for that nice introduction. I appreciate that very much. I'd like to start with a couple of thank yous. The Provost office has been really helpful in solving some of the math problems in getting this talk together. Claudine Chelier and Skye McKeever. Actually, Skye designed that lovely poster. I don't think she's here. And also, thanks to Provost Brown for inviting me into the series. I really appreciate that. Just bear with me for 1 sec while we change. Do a quick change up. One other thing I just wanted to mention, and it's not a little thing. I tried to design this talk so that it would be accessible to 8th graders, tweens, all the way up to centenarians. And we actually have a centenarian in the audience tonight, and it's Emma Lomason. And I'd just like to recognize and thank Emma Lomason for coming to this talk. She has... If you're a new student here, you know there's a building named after Emma, and if you've been around for a while, you know that Emma was an assistant in the Department of Mathematics years ago, and was the assistant to the longtime chair at that time, and that chair built a house that the current president lives in. So Emma has a lot of ties to the university, and I called her to invite her, and I kind of knew she had a soft spot for mathematics in her heart, and as it turns out, it was a soft enough spot that she came to my talk, and I'm really honored and privileged to have you here, Emma, and I'm also really privileged to be speaking to this whole audience. So let's get started. I have here a belt that I went and bought at the Trailhead for this demo here. Fits me pretty well, see? Tight. Okay. What I'm going to do is add a yard or a meter or so of length to that belt. Can you hear me okay? Everybody hear me? So I just added, depending on how you like to measure in metric or otherwise, I added about a meter to that thing. And you can see it adds quite a bit of slop, right? You see? It's about that much slop around my girth, okay? Now, I'm going to introduce you to the earth girth problem. So we're going to do the same thing with the earth. We'll take a red strap and wrap it tightly around the earth and open it up, open the strap up, once it's nice and snug, open it up, and add this to it. The same piece, same length, exactly the same length. The problem is, how far above the Earth's surface is a longer strap? Does everybody have one of those little slips of paper that my helpful assistants were passing out when you came in? What I'm going to have you do is fill in what you think intuitively is your best answer to this question. So the answer is 5.73. But that's just a partial answer, right? The multiple choice part is, what are the units of that? When you perform this experiment, is it going to be practically imperceptible? You can't even see it? 5.73 thousandths of an inch? Or 5.73 millimeters? About like so? Well, it's half a centimeter and a bit. It'll be like that. I'm talking about spread it evenly around the earth. You understand? Any questions on this? Will it be centimeters or inches? Okay? That's the question. I want you to fill out those slips with the best answer that you think, but don't sit there and do calculations. Just use your intuition. I want you to use your intuition. This is an intuition quiz. And then, as I'm talking in the next few minutes, that my trusty assistants are going to be wandering the aisles and collecting these slips of paper, and there's going to be a fabulous prize. Now, that's my daughter. She's 6, and she helped me make that pie on the weekend. And both my kids kind of wanted to be in the talk, so I said, okay, you can be in with the pie. More on the pie later. So get these slips done, and assistants, so mill around, get it. I'm going to continue with the talk, okay? So I think it's time for the wardrobe change. Start by talking about a little bit about geometry. So there we have a square, and I marked its diagonal, D. That's the diagonal of the square. And can you see that dot? I want to get the perimeter of the square in terms of the diagonal, okay? And I'm going to go through this kind of quickly. Don't feel frustrated if you don't follow every little step. I'll explain it once, but actually understanding what I'm saying in this little explanation will not hurt you later on in the talk. So we're going to use the Pythagorean law, and that's one side, and it's a square. So this is a side that's equal to that first side. And side squared plus side squared, the top side, is going to equal d squared. So 2 sides squared is d squared, and d is the square root of the side. So square root of 2 times the side. D is the square root of 2 times the side. So to get the whole perimeter, it's going to be 4 of those. But that's D. I need to get S. So that side is D over the square root of 2, right? D over the square root of 2. And then 4 of those will be 4 over the square root of 2 times D. I'm going to use C for perimeter because I'm looking toward thinking about circles in a few minutes. So C denotes the perimeter because later on I'm going to be thinking about circumference, and I don't want to keep changing notation. So the circumference of the square in terms of that diagonal is 4 over the square root of 2 times D, and this comes from the Pythagorean law. I talked my way through it a little bit. I hope I didn't lose you, but if I did lose you, don't worry. The point is that we get a number. The perimeter is some number times that diagonal. And it doesn't depend on the size of the square, right? It's just whatever the diagonal is, the perimeter will be 4 over root 2 times that diagonal. Similar kind of calculation on the regular pentagon. If you look at the diagonal, I'll call that D2, you'll wind up with the circumference or the perimeter being 10 over 1 plus the square root of 5 times D. It doesn't, how I got there is not that important for the talk, but it turns out to be a beautiful fact of pentagons that take a side, the diagonal there will be the golden ratio times the side, if you know what that is. And if you don't know what that is, it doesn't matter. So you end up with 5 over the golden ratio, which is 10 over 1 plus the square root of 5, for the perimeter. Again, we just get a raw number times D to get that perimeter. I'm going to do this one more shape, regular hexagon. If you play that game, for the perimeter you get 3 times the diagonal. And that one's quite easy to see because you just put in 3 diagonals and use the equilateral triangles that it cuts that into to show that the 3 diagonals are exactly equal to the perimeter. So just to summarize what I've been saying, if you take that ratio, circumference or perimeter, divided by a diagonal for these various shapes, you get a raw number. You get a raw number for a square, 4 over the square root of 2. You get a raw number for the pentagon, this thing. You get 3 for the hexagon. And those numbers are all about 3, all approximately 3. What do you think would happen if we put circle into the list? Well, I'll give you a hint. So, as I said, my kids both wanted to be in it. So now you can see that they both got in it with pi, right? Incidentally, there's a nice sculpture garden in Port Townsend, Washington, where that picture was taken this summer. Well, you guessed it, and I think you saw where I was going with this, the circumference of a circle is pi. The magic number that goes in place of all those other fractions I was putting there is pi for the circle. Now when I learned this formula, and I think probably almost everyone in this room has at some point been taught this formula in school, it was taught algorithmically to me. It was explained that anytime you want to get the circumference of a circle, you just take the diameter of it, multiply it by pi. Like, that is something I'm going to need in my life. Someone's going to walk up and say, here's a circle, here's the diameter, what's the circumference? I can honestly say, now, I'm a mathematician, for crying out loud, and I can honestly say that I have not in my day-to-day life ever used that formula algorithmically like that. Now, I'm not trying to make an argument that that is a useless formula. It's not a useless formula. But I think in that form, and presenting it to people like, this is a good algorithm to learn, sort of misleads people about what's going on here. So I just want to talk a little bit about pi. Now, back when I learned that formula, they told me it was 22/7. Does anyone recognize that fraction from when they were in 4th or 5th grade? Well, pi is not 22/7. It's approximately 22/7, but you can't write pi. You can't express pi as a ratio of integers like that. But by the way, while we're at it, I will mention, that ratio is a lot better. 355 over 113, and I finally figured out a mnemonic to remember that fraction. It's all the odd numbers, right, from 1 to 5, and you just line them up, 1, 1, 3, 3, 5, 5. It's a visual, so you can remember that, 1, 1, 3, 3, 5, 5. That's a very good approximation of pi. You're writing down six significant digits there, and it gives you pi to 7 significant digits, by the way. So if you want to use fractions for pi to approximate pi, use that one instead of that one. But it's a fact that you can't express pi as a fraction like that. So then the next year we changed textbooks, and pi wasn't 22/7 anymore. They said, okay, no, pi is 3.14, and they also taught us to use decimals. So pi is 3.14. Also not true, right? You all know that pi goes on and on and on and on, never repeats. I could fit 41 digits of pi on there, but that's a lie too. Pi is not equal to that. Pi goes forever on after that, never repeats, can't be expressed as a ratio of integers. Actually, you can't even write down pi as a solution to an algebraic equation. They call it a transcendental number. And I just want to do a sort of quick trip down some formulas to kind of convince you that pi has intrigued mathematicians for a long time. This is a formula that was known to Leibniz, the inventor of calculus. It's often called Leibniz formula for pi. And at this point, I just want to point out, it's a good place to point out that there's a nice pattern there. It's plus, minus, plus, minus, plus, minus, like that, and then the odds on the bottom, 1, 3, 5, 7, 9, like that, alternating. That, if you add that, people who study calculus can figure out how to add an infinite number of terms like that. And if you add it, it comes out exactly to pi over 4. So that really is equals. And that's been known since the 1700s. And the point that I want to make about the patterns was mathematics isn't really about numbers. Mathematics is about patterns. And there we have a really beautiful pattern for pi. I'm going to show you just a couple others. Really, this is just to convince you, and you probably know this already. Mathematicians really have been sort of obsessed with pi for a long, long time. That's a formula that was known to Euler, also from the 1700s. He solved a big problem. He became quite famous with the solution of that problem, to show that the sum of the reciprocals of the squares of the integers comes out to pi squared over 6. This formula here is actually predates those earlier formulas. It's another neat one. 2 over pi is this infinite product. This formula here was proved and published in 1995. So back to the 1700s and even into the 1600s, and then 1995. Probably most of you were alive then. I mention it because this was a big breakthrough in recent computer computations of pi. It allows people to, this formula, I won't explain how, I don't actually know how, but it allows people to compute arbitrarily far out in the expansion of pi without having computed earlier on. So you can just jump. If you want to start computing at the millionth digit of pi, you don't need to know all the earlier ones. You can just go straight to those using this formula, and they do it in hexadecimal, and that's, hexadecimal means base 16, and there you see the power of 16. So that's turned out to be a really useful modern formula for computing digits of pi, and people use, it's not really a useful thing to do except to test computers, test computational power. Just a couple more formulas. This is Wallace's formula for pi. Pi over 2 is you can see the pattern, another beautiful pattern for pi. I just will tell you one quick anecdote about Wallace's formula. I was taking a combinatorics course that mentioned Wallace's formula in the textbook, and the prof said, does anybody know what Wallace's formula is? I wasn't sure what that meant, so he came across it too and he didn't know what it meant. Then the next class he said, did anybody look up Wallace's formula? And no one had. And he said, I guess there are no A+ students in this class. Nobody looked up Wallace. So I did not get an A+ in that class. There's a continued fraction for pi. This is root pi is that, whatever that's an integral. It's an area under the bell curve. You draw the bell curve and then compute its area. You get root pi. That was known to Gauss. Until the 1980s, this formula and relatives of it that use inverse trig functions for pi, that was the one that was used to get computer computations of pi way, way out. And then some breakthroughs in the 1980s, and then that formula I showed you from 1995, people switched over to that one. Anyway, I don't want you to think about pi in all these beautiful ways. I want to just go back to basics. Think about it this way. So we had the formula written in the algorithmic form, C equals pi times d, but you can rearrange it so that pi is C over d. And I wrote it nice and big, and I want you to stare at it and get it into your head, because you are staring right now at the algebraic version of the entrance of pi into human consciousness. That is what pi is. And this was known to the Babylonians. This goes all the way back to the Babylonians. They noticed that it doesn't matter how big the circle is. You know, a circle this big, a circle the size of a pinhead, a circle the size of the earth. It doesn't matter. That ratio, C over d, is always going to be the same number, and we call it pi. Any questions? So we get to add the circle to the end of the list, and I would now like to use it for something. So we're going to solve this Earth-girth problem. So my trusty assistants, could we make sure we get those slips collected? Have they already been collected? Yes? I have all the slips? Okay, great. We'll do the drawing later. So there's the Earth, and I'm going to use that formula to solve the Earth-girth problem. I've got C, circumference old, and diameter old. So that's, the red is meant to remind you of the original belt, okay? The original belt was red. When I was making these slides, I showed them to my wife sometimes, and she said, my wife Jennifer, hi Jennifer, she said, see, people are just going to read that as cold and dulled. So she's probably right. It's circumference old and diameter old, okay? And the relationship between those is this one that I'm going to keep talking about. I've rearranged the formula yet again C equals pi d, right? C equals pi times d, but you can send pi downstairs, so express it this way. So the old diameter and circumference are related that way, and then we're going to pull the belt out away from the Earth's surface like that. Can you see the purple? Does it show up okay? And then we got a new circumference and a new diameter. That's my notation. And those are also going to satisfy this relationship of the relationship defining pi. Now we're going to do some calculations, okay? So solution to the Earth girth problem. There's a standard relationship, repeated again, d equals c over pi, and we're going to start with the new. D new equals c new over pi, right? But what's c new? The new circumference, it's this thing that's been added to the circumference, right? You added a meter or so to the circumference. Well, I'm going to call it 36 inches. We'll call that the c old plus 36 inches. And you break the fraction up, c old over pi plus 36 over pi. And I'm going to make that blink there. You see c old over pi, the red stuff? Look right above. C over pi is d. That's a d. So that'll be, the red stuff there will be d old, right? C old over pi is d old. And then 36 over pi just stays there. You following me? So all that internal stuff, quickly erase that and zip them together. Okay, that's what we got so far. D new equals d old plus 36 over pi. Now we're going to bring in that pi is about 3.1415926, like that. And that comes out, 36 over that number is 11.46 inches, okay? So that's what we know now. We're almost done with the solution. We got the relationship between the new diameter and the old diameter. They're off by almost 12 inches. Divide everything in sight by 2. That'll give you the radii. So this d new divided by 2 gives you the radius new. D old over 2 gives you radius old. 11.46 over 2 gives you 5.73. That's the number from the answer key, right? Everybody showed you the answer key? The strap will be almost 6 inches above the Earth's surface. Can you believe that? I want to know who's surprised by that. Is anybody? So, I remember somebody told me this problem when I was about 20 years old, and I didn't bother to solve it. I just heard about it, and I didn't know what the answer was. And I told it to some physicists at the National Research Council labs in Ottawa, and so they were my supervisors, and they didn't believe me. So then I actually worked it out, and they couldn't believe it either. And I mean, it's really kind of shocking. I mean, I've been talking about this problem on and off, mostly off, but for 30 years. It's really shocking. It just defies our intuition. So that's not to scale. Of course, it's not that far off the Earth's surface. But it's about 6 inches. Did you follow the reasoning there? And it all comes down to that formula. The definition of pi. And I wanted to talk about this problem as kind of the warm-up, because there aren't too many formulas in mathematics that are much simpler than that. It's just one quantity is a constant times another. It's about as simple as you can get in terms of mathematical relationships. C is pi times d, or C equals 2 times d, or 3. Those sorts of relationships are the simplest sorts of relationships. And the solution to the Earth's girth problem, comes down to this one. And we all knew this formula. We all learned it at one point in our life. But it didn't inform our intuition. It had no effect on honing our intuition so that we could just answer that problem off the top of our head. I mean, now that I showed you the calculations, it's fairly transparent. It's just, if the addition is 36 inches, the addition to the diameter is going to be 36 over pi, which is about 12 inches, because pi is about 3, right? So it's remarkable to me that we could, and it's me too, it's everybody, almost everybody you talk to about this problem, that it defies, it really shocks their intuition, and yet it's such a simple formula. And there are formulas, in modern formulas, that really profoundly impact our lives. I'm thinking about formulas that involve climate or weather, or formulas to do with data encryption, or formulas that are related to DNA, life, the encryption of life, sequencing DNA. There's all kinds of mathematical models and relationships. And they are way more complicated than that. I mean, like I said, that's about as easy as they come. So it's sort of a plug to keep mathematicians around, because these sorts of things, they need to be studied. They need to be studied by people who can actually refine their intuition and human understanding of these important things, problems that come up around us. So welcome to Missoula, Montana, where we gather in the music recital hall and talk about pi, or listen to somebody talk about pi. This is like a break slide. I have a $20 bill in my pocket for the first person who can tell me where that sign is. And we'll do it during break time. When we're milling about eating cookies or whatever's out there. I put an extra 20 in my pocket. You have to tell me within, say, a football field, okay? If you can tell me within a football field of that sign, tell me, maybe describe, what road is that? I can walk up to it, I guess. What road is that? Where's that ditch? You don't have to say all the features, but I want to know, like, what intersection or something about that within a football field, okay? Does anyone recognize it? My straight man's over there. Okay, so this talk is actually divided into 3 segments, and you've seen the first segment already. It's on pi. The way I constructed it was, the other 2 segments are 1 and 2, okay? Remember from the title? The way I constructed it was, I wanted to put a problem in there that's kind of intriguing and defies our intuition, and it's fun. You can take it to parties and tell people. I wanted to talk about my research a little bit, and that's 1. My research is going to be on the number 1. And then I wanted to talk about my teaching a little bit, and that's the 2, okay? So here we go with my research. Segment 2. Actually, before I go away from this slide, I just want to sort of fess up. This is not an applied mathematics talk. I said we're going to talk about mathematics of planet Earth. Well, that was a little bit of a lie. You've seen the planet Earth segment, okay? It was the Earth-Girth problem. I'm not going to talk about Earth anymore. And I feel like I didn't really do it justice, because actually it is currently a special year in mathematics research called Mathematics of Planet Earth. If you Google that, Mathematics of Planet Earth, you'll see there's all kinds of activities and conferences and seminars and gatherings to do with mathematics of planet Earth. I mean, to understand things like climate and stuff, and I didn't do that, and it was a bit of a bait and switch. But this talk is really about, I'm a pure mathematician, and I'm really interested in applied mathematics, but it doesn't happen to be where I do most of my work. So I wanted to make this a personal talk and show you some things that are really nifty to me. And there isn't much in the way of really applied mathematics. It's just nifty, cool things about numbers and patterns. So here we go with the number 1, our study of the number 1, okay? This warm-up slide should be easy for pretty much everybody here. So we're going to look at powers of 1, right? So 1 to the 1 is 1. 1 to the 10 is 1. 1 to the 100 is 1. Deep facts about the number 1, okay? That last number is a googol. 1 raised to a googol. 1 with 100 zeros after it. That's still 1, right? It goes on like that. You're never going to get anything different on the right-hand side than 1. Everybody knows that, I hope. So let's get more serious. I'm going to change the base from 1 to 1.01 and look at those powers. So 1.01 to the 1 is 1.01. 1.01 to the 10 is not very big, 1.104. To the 100, it's 2.7 something. And to the 1,000, now we're getting serious. So it's almost 21,000. So 1.01, raise it to the 1,000th power, you got almost 21,000. Take it to the 10,000th power, and you have a number 44 digits long. And the 100,000th power, 433 digits long. More than 4,000 digits long, if you keep going with this. So what you're witnessing here is, depending on the way you want to say it, the power of compound interest or exponential growth. You can call it. I was using Mathematica, this mathematical software package called Mathematica, which I don't know how to use very well, but for this talk I thought I should use Mathematica to get some facts. So I took 1.01 to the Google, and it couldn't distinguish between that number and a Googleplex. So a Google is one with 100 zeros after it. A Googleplex is 10 raised to that power. So there you see, there, right there. That's a Googleplex. 10 raised. Now that's actually not exactly equal to this, but Mathematica couldn't distinguish between 1.01 to the Google and 10 to the Google. Okay, there's a little bit deeper facts about the number 1. I am going to tell you about something that happened a long time ago, 100,001 years ago. I was playing with that calculator. You think I'm joking, but this is binary. That's in binary. It's exact. Okay, it's exact in binary. You can probably deduce my age little by little from the comments I make. So I was playing with that calculator. I didn't go and photograph my calculator. You can go to the web and get pictures of old calculators. So I did that. And that's the calculator I was playing with. And I'll just point out, it's got a log button there. That's the natural log button. That'll be important in a minute. But what I was doing was trading off the 2 power experiments that I just showed you. I loved playing with my calculator, by the way. I just thought it was so cool that a piece of equipment could do all these calculations. And I'm from the generation where kids just about 5 years older than I was were doing all their calculations on slide rules. So like physics students and math students who were in seniors in high school when I was in 8th grade, they were working with slide rules. And by the time I got up there, it was calculators like that. It's just kind of amazing. So I loved it, and I played with it. And I did this experiment. Raise 1 to the 1, just like the first guy started. And then I'm going to raise the next thing to the 10th, but I'm going to add a little bit to the base. So 0.1. So this was just nothing, and then I added 0.1 to the base, and I bump up the exponent. You get about 2.5. Then I'm going to bump the exponent up, just like I did in all those other patterns, but I'm going to add a little bit less to the base. So instead of being 1.1 to the 10, it's going to be 1.01 to the 100. And then go like that. Do that pattern. 1 in 1,000th raised to the 1,000th. Like that. 1 in 1/10,000th raised to the 10,000th. So you see the exponent there. That exponent is the reciprocal of the thing you're adding to 1. It's 1 plus a bit, and then you raise it to 1 over that. 1 over 1/100,000th is 100,000. But look what's happening on the right-hand side. It's not going to 1, like my first example, and it's not blowing off to infinity, like my second example. It's settling down on a number that many of you will have seen it before, and many of you will have not. 2.7182, settling down like that. 82. I did Mathematica on it. I did 1 plus 1 over a Google, raise it to a Google, and I got 2.7182, 818284, like that. It's kind of astounding that happens. It doesn't go off to infinity, and it doesn't go to 1. It's perfectly balanced. And so it just settles in on one number. I showed that to my teacher, and I knew that was the inverse natural logarithm of 1 from my other playing. I was playing with the calculator, remember? So I had figured out inverse natural log of 1. I came out with that number. And then my fooling around with powers of 1 came out with that number 2. And he just shook his head. He didn't know what to tell me. But this is quite an important number in mathematics. They call it E. So E is called the limiting value. If you were to just carry that experiment on forever, it'll settle in on this 2.71828182, blah, 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 like that. I made it look like that pie slide because these numbers have a lot of things in common. Pardon me. So there's E. I used to think E was for exponent until I prepared this talk. And I found out, no, it's not. It actually it's given from the name Euler. It's named after the mathematician Euler, who was born in 1705, I think, or 7, or early 1700s. He just turned 300, or his corpse just turned 300 a couple of years ago. So that's the result of I came upon this number just with my own fooling around on the calculator, and eventually I came to know that it's really quite an important number. And so I'm going to show you some of the important features of this. And one of them is in calculus, important features. But I'm not going to talk much about calculus today, but I can't resist showing you kind of the most famous thing about E. So there we have a graph. And this is convenient. So I'm graphing, remember how these go? I graph x versus e to the x. So the e there, that e up there, is the e that I just introduced to you, the 2.7 number. And the input's x on the horizontal, the output's e to the x. And what that means is any place I go on the base here, let's say at 1, let's say I use my hand, at 1, the height I rise here, I can check over here. See, it comes in, there's 3, and there's 2.5. It comes in at 2.7182818. That's e to the 1. And it's like that all the way along. If you go here, this will be e, you go up this high, it's e to the 2, which is a little over 7. And if you go here, this is 0, e to the 0 is 1. See, it cuts right through at 1 here. So that's how you make a graph of e to the whatever power. Well, this curve has some pretty interesting properties. I'm going to talk about these tangent lines. So there, I put a few tangent lines on there. Let's look at that one. Remember slope? Slope, I think a lot of you will have forgotten slope, and some of you won't, so don't be insulted if you remember slope. Slope is a measure of the steepness of the line, and it's measured as you take how much the line rises, and you divide it by how much it runs. Like I call it rise over run. So this red one, if you extended it down here, it actually hits right at the -1. And it rises all the way up to, this is exactly 2 here, where it is. And so it rises from 0 up to 2, and it runs from -1 to 1. That's also a run of 2. So that thing has slope 1, because the rise is 1 divided by the run is 1, so slope 1. That's a measure of the steepness of the line. So that guy has slope, the red one has slope 1. So that's the tangent line to this blue curve, right at the point where the curve goes through the vertical axis. And I got a bunch of tangent lines. So there's the tangent line, a little steeper here. It's the tangent line through the point 1e. 1e to the 1, right? 1e. That's the tangent line. That guy's slope happens to be e. The slope is, the value of the blue thing is e, and the slope is also e. And over here, at -1, this slope, the rise over the run of that thing, is 1 over e. Turns out to be 1 over e. This slope is even shallower, 1 over e. And the value of the curve right there is also 1 over e. It's like that. It's like that for the whole thing. Every place you go and graph it, the blue value of the function is equal to the slope of its tangent line. Everywhere. There aren't too many functions or curves in mathematics that do that. This is the only one, actually. If you take e to the x, or 5e to the x, or 10e to the x, or 3e to the x, this family of functions that are some multiple of e to the x, they are the only ones in the world, in the universe, where they self-describe themselves in terms of slope. So their height, the blue height above the horizontal axis, is exactly equal to the slope of the tangent line along there. It's sort of, like I said, self-descriptive. And that is really important. That's an important property in calculus, differential equations, all kinds of modeling. This comes up. It's not the thread of my talk, but I couldn't resist telling you about that. This basic property of E. So it has a kind of a continuous flavor. I should go back one. This is continuous mathematics. We take the continuum of the real line. This is like the points are all spread out in one continuous smear, and we bend it up into the blue. That's a continuous curve, and that's the subject of continuous mathematics that's used to measure things like temperature and height and things that can be measured along continuous scales. But it turns out that E also has a role to play in counting problems. So in the introduction, Jenny mentioned that combinatorics is sort of about counting. So I'm going to talk about counting now. And the thing I'm going to count has to do with these things called trees. So let me introduce the concept of a tree, and then we'll do some counting. So here is a network diagram. These little circle things are called vertices or nodes, and the blue arcs connecting them, little segments, are called edges. So you see these pictures when you open up flight magazines, and they show you the route maps of whatever airline you're flying, right? You see the nodes are the cities, and all these arcs are the connections between them. So these come up even in magazines that you might read on the airplane. This is a special type of network or graph called a tree, and what makes it a tree, I'm going to now tell you. One is it's a connected thing. So between any two of these nodes, I can get around along the blue edges via a path. And that wouldn't be true if I let's say I took this one out. Just remove it. Now it's not connected anymore. This piece here falls off. Okay? So that thing now is not a connected network, so it's not a tree. So let's make it connected again. So that one of the defining features of a tree is it's got to be connected. And the other one is it's got to be minimally connected. You can't have redundancy built in. So here I put a redundant edge here. I added a redundant edge. And now, between these two nodes, I can walk around the outside and get like that, from there to there. Or I can just go along that new edge that I added. That's called a cycle. I was going to say circle. That's called a cycle in the graph. And you're not allowed to have cycles in trees. So take that out. And if you add any other arc anywhere, it'll create a cycle. So I put one more sample up there. So there's a new arc I added, and see that creates a cycle. So trees, the two defining features of trees, aside from being one of these node edge networks, is that they got to be connected and have no cycles. Okay, connected and no cycles. Those are the two key features I need. Now I put a really complicated one up there so I could give you lots of examples to do with it, but we're going to be looking at small examples. So here's a tree with 4 nodes, and I should point out that this is not a geometric concept. I'm drawing it on a screen, and it looks like geometry, but if I were to move that node and put it over there, and then redraw the arc to it, it would be the same tree. What's important for trees is just the incidence relations between the nodes. So I've got, this one has 4 nodes, and one of them has 3 neighbors. Those are called neighbors. And those 3 neighbors are all just attached to it and it only, and that's the tree. And I could redraw it many different ways, but that's one of the 4-node trees. And there's another one. That's another 4-node tree. And if you think about it, if you if you start to space out here, get out a piece of paper and doodle this, those are the only two four-node trees you can find. Up to this moving stuff around that I talked about, but I'm only interested in the incidence relations between them, and that is, this one has 4 lined up in a path, and this one doesn't. And how are they connected? They're connected this way, and that's it. So if you make some sketches, you'll see that those are the only possible ways you can do it for 4 nodes. So those 4-node trees are those ones. I started with 4 because there's only one way to do the first 3. So a 1-node tree looks like that, a 2-node tree like that, and a 3-node tree, a path like that. It does get more interesting at 5 nodes. So there's a path on 5 nodes, analogous to the paths up here. And there's that's called a star, actually. And that's analogous to the very first tree I started to look at. And then on 5 nodes, there's enough wiggle room that there's one other shaped tree you can do. It looks like that. So that's the third type of tree on 5 nodes. So here I am, I'm counting up the possible number. So on 1 node, there's 1 tree, 2, 1, 3, 1. The sequence goes 1, 1, 1, 2, 3. And we could figure out 6 and 7 and so on. But it turns out to be quite a difficult problem to count. If I say, how many trees are there on n nodes? There is not a nice, concise formula for that. So what would be the next in the sequence? Could I give you a formula that would give you the 6th and the 7th? As far as I know, nobody knows a formula that's like that. But if you make things more complicated, there is a nice formula. And that's what I want to lead up to right now. So I'm now going to distinguish between trees with different labels. So I can take a tree on 3 nodes and label it like that, 1, 2, 3. Now the nodes have names. They're different. So there's a couple of other ways you could put the labels down. I could put them down 1, 3, 2, or 2, 1, 3, like that. Now those are distinct labeled trees because the edges in this one, say the first one, are 1, 3, and 3, 2. And that is not what the edges are in that second one. Here they're 1, 2, and 2, 3. Well, 2, 3 is there in the first one, but 1, 2 is not, right? 1, 2 that's a new edge. And we lost the edge 1, 3. So those are distinct labeled trees. And the third one is also different from those first 2. Now, if you're sitting there thinking, yeah, but I can rearrange the numbers 1, 2, 3 in 3 other ways. I can think of like 3, 2, 1. What about 3, 2, 1? What about 3, 2, 1, like that? 3, 2, 1. Well, that would have the edges 3, 2, and 2, 1. That's exactly this tree. 3, 2, and 2, 1 is already taken care of. And the sequence 3, 1, 2, if I wrote that down, 3, 1, 2, it would look different than those sequences, but it would just give me this tree again, because I'm only interested in the incidence relations between them. You see, you get the distinction here? So there's 3 different labeled trees on 3 nodes. And back up to I started on 3 because the earlier cases are too easy. So on 2 nodes, there's only 1 labeled tree with 2. And on 1 node, there's 1. On 4, things do start to get more interesting. There are 4 like that. So you remember this shape. This was the very first shape I looked at with 4-node trees. Now, let's look at the number of ways to label it. I have 4 choices. I can either put 1, 2, 3, or 4 in that spot right there. And then once I make that choice, everybody else is just adjacent to 1 vertex. So that's called a leaf. Remember this word. A node that is adjacent to just 1 other vertex along an edge is called a leaf. We're going to need that a little bit later. So there are 4 ways to label the 4-node tree that looks like that shape. And I'm not going to go through the details, but there are 12 ways to label the 4-node tree that looks like that path. So that's one of them, 4, 1, 3, 2. And there's actually 12 different ways to put those. So if you get a total of 16, 12 plus 4, 16 labeled trees on 4 nodes. 5 nodes, I won't go through the details, but there are 60 ways to label a tree like that, 60 ways to label a tree like that, and 5 ways to label a tree like that, for a total of 125. So the sequence I get for number of labeled trees on the various number of nodes is there's 1, then 3, there's 3, the next one's 3, then 16, see, 12 plus 4 is 16, and then 60 plus 60 plus 5, 125. That's the beginning of the sequence. So I showed, so there, I've written those numbers down. 1, 1, 3, 16, 125. If you did the 6-node trees, you'd get 1,296. So let's see what the pattern is. I showed this to my kids when I was making the slides, who are 6 and 7. And when they saw that much of it, they got it. So I think you'll probably get it too. What's the next one? 5 cubed. Right, 5 cubed is 125, and then turns out 6 to the 4th is 1,296. And conveniently enough, actually, 1 fits the pattern too. It's 1 to the negative 1, right? So the general, so this was actually proved in the late 1800s, that the number of labeled trees, if you just tell me how many nodes you have, let it be n, the number of labeled trees is always n raised to 2 less. It's a beautiful, the man associated with that, the mathematician, who happens to be a man, is Arthur Kayll. So that's called Cayley's formula for labeled trees. It is absolutely astounding how simple that is. I personally think this is one of the most beautiful formulas in mathematics, because you've got so much complexity here. Look, that 125 number, it doesn't come about from a simple 5 cubed. That's not where it arises. It comes from 60 plus 60 plus 5. And each of those takes a bit of doing to count. Well, this one's easy to count, but these other ones are kind of tricky to count to get those numbers 60 and 60. And, you know, put down an n-node tree and imagine the complexity. Remember the first tree I put up there, really complex. And the number of ways to label it, and the number of labeled trees with that many nodes was whatever its node count was, raised to the n minus 2. That simple formula right there. It's just completely amazing. I mean, I could jump up and down about this all day. It's completely amazing that this complexity boils down to such a simple formula. So I think a lot of other mathematicians have really enjoyed this formula too, because there's about 20 published proofs of it. So the first one was in, like I said, 1889, I think. And I, with my first PhD student, actually published a proof of that just appeared in a journal this year. So I said this is the research segment of my talk. I am lucky enough to have published a proof of that. I won't get into the details of how we did that, but I'm on the list now. But don't you think that, I mean, I won't. Okay, so here, what does this have to do with E? So here's an experiment that you could never do, but you can imagine it. This is a thought experiment. So you take a brown paper bag, and you fix n, the number of nodes, and you fill up the bag with all the labeled trees, all n to the n minus 2 of them. We know that's how many there are, right? You put them in there. Now, don't look too carefully, because I got a lot of duplicates. I'm not thinking of really having duplicates. I'm thinking of having all the n to the n minus 2 labeled trees, stick them in the bag, and 1 each, okay? So I did it with 5 here, and I didn't really get all 125 trees. It's just to convey the idea. But here's the experiment, okay? You reach into that bag, you grab one of the trees at random. So just reach in the bag, grab a random tree, and now, having made that choice, pick a random node in the tree. So maybe I pick 5. Maybe I pick 3. Any choice, any of those 5 nodes, you just randomly pick a number between 1 and n, and that's it. So my graphic just shows those 2 choices, but it could be, you pick any of those 5. And so do you understand this? You put the trees in the bag, you reach in, you grab a tree, you pick a node like that. Remember, nodes that just have 1 attachment are called leaves, okay? So my question here is, what's the chance that the chosen node is a leaf? So you do that probability experiment. What is the probability that the chosen node is a leaf? I don't have any slips for this one. It's 1 over E. Okay? 1 over E. And okay, so it's not exactly 1 over E, but if you let n get big, they call it, it converges to 1 over E. Whatever the probability is, it gets closer and closer to 1 over E. And so 1 over E is kind of the magic number associated with this experiment, because it is the number that all these probabilities I'm talking about zero in on as n gets big. Now that is really bizarre, because remember I said that this is E is to do with continuous things. Calculus, curves, slopes, things like that. And here we have E popping up in essentially a counting problem. This problem, what's the chance that the chosen node is a leaf? You just count up all the ways of doing that experiment, grab the tree, reach in, put it down, then all the ways of picking one of those n nodes, put that in the denominator, the bottom of the fraction, and then on the top, count up all the ways that experiment could turn out with a leaf. And the fraction turns out to be about 1 over E, which is, by the way, about 36 or 37%. So it's about a 36% chance that the chosen node is a leaf. Okay, new problem. I finally got internet at my house this summer, and I found out you can get a lot of cool stuff on the internet. So I downloaded this Monopoly guy, and then I made this picture. I'm quite proud of it. Each one is 90% the size of the previous, and then I just lined them up so that it looks like they're getting further away. I have no training in art at all. I have a friend in the audience who has training in art. But the hat check problem. So this is a 300-year-old problem. So I'm gonna say it sort of in the language of that time. So there aren't any women in this problem, but don't take offense to that. It's an old problem. It really does come from the early 1700s. The problem is this: a bunch of men with hats who are not clones. Okay, so they're not supposed to all look exactly like each other. The hats are distinguishable. The men are distinguishable. They show up at a party. They check their hats. So the hats are all different, right? They go to the hat check room. They check their hats. They party away. They come back at the end of the party, and they want their hats back. But the hat check person has been drinking, and she's completely inebriated, and she just gives the hats back completely at random. And I want to know, what's the chance that no one gets his own hat? Okay? So this is old. This is called Momar's hat check problem. Momar was a French mathematician. And the answer is 1 over E. Isn't that weird? So it's another, you can go back there and count up all the ways they could get their hats, and then it's n factorial. If there's n people, there's n factorial, n times n minus 1 times n minus 2 all the way down to 1. Ways to get the hats back, and then you count up all the ways the hats can go back where everybody gets a different hat. You form the fraction, and if n is big, this is again, it's an approximate thing. If n is big, it converges on 1 over E. So I don't have a graphic to take you back to the continuous, but this is another example where we have a E popping up in a counting problem, and it's pretty weird. Okay, here's another problem, the kindergartner's field trip problem. So I made up this problem. In April, I was working with a really good undergraduate student named Lauren Morey, and she was working on a senior thesis, and I had her, with my help, and she did a lot of it, she came up with a new proof of this counting formula that was kind of abstract. And I said, we got to come up with a problem. All year long, I kept saying to her, we got to come up with a problem to throw your theorem at and count. And in April, it might have been March of this year, I woke up in the middle of the night. This has only happened to me about 3 times in my life. I woke up in the middle of the night, and I had it. This was the problem. And I was right, and I couldn't sleep anymore, and it was a Saturday night, I woke up and just started working on it, and I pushed it through, and by noon of Sunday, I had discovered, yeah, this is it. This is a perfect problem to put with Lorentz theorem. And I'll tell you a little bit more about that in a second, but let me describe the problem. So the problem is this. You've got these kindergartners, and when they go on field trips, they always have to go in the buddy system, right? So they're paired off in their buddies, and they go off on a field trip, but they have their teacher is actually a student teacher, and she makes the rookie mistake of setting them loose in the library and not telling them they have to get back with their original buddy. So they just buddy up completely at random at the end of the day, and they come back. So now she gets in trouble from her supervising teacher because they lost somebody or something like that. So the question is, actually they didn't really lose anybody. The question is, so they get back, everybody has a buddy, and I want to know what's the chance that all the buddies are different? What do you think? I hear somebody anticipating the answer. Is 1 over the square root of E. So this, I was so happy when I found this out. I thought, this is great. I'm going to get a paper out of this, and so was Lauren. And I worked on it. I was describing this before on Sunday and then Monday, and I had it all done. I thought, I better check this on the internet. And again, it's approximately a pen this big. Check this on the internet, and it turns out it's been done. Not in the guise of the kindergartner's field trip problem, but the basic problem of instead of hats, replace the hats by people, and then the problem of hooking people back up so that they're all different. It has been thought of. It's actually thought of, it's kind of a timely thing to tell you about, because it was originally thought of because the US Open tennis tournament, one year, people complained about the scheduling, and so that they rescheduled it. And some of the original tennis partners were repartnered, and someone complained about that too. And then so some mathematicians got involved, and they wanted to know what was the probability of no original partners being put back together. So it's sort of like it's the kindergartner's field trip problem. And so, but it was just around 2000 this came up. The year 2000. So you've got the hat check problem that goes back to the early 1700s, and then this field trip problem. I'm the one who named it that, but the idea just came up in the year 2000. So all was not lost. I couldn't publish it as a new thing, but no one had noticed this proof of it. So I wrote it up. I squeezed it onto one page. I did all I could to get it onto one page, and I sent it to the most widely read mathematics journal in the world. It's called the American Mathematical Monthly. And usually, you should know in mathematical publishing, well, you shouldn't know this, but I'll tell you, it can take a year or a year and a half before you get a reply back about your paper. It takes the referees a long time to check the details and that. I got a reply in 10 days. Dear Professor Kayll, the editors like your piece. It's going into the queue. 10 days! So all was not lost. And Lauren also got her paper published, by the way. Just learned that 1 week ago. So how are we doing here? That's the continuous stuff. It's really weird that E keeps coming in counting problems, it being a continuous parameter. But that's all I want to say about E. So we're done with segment 2 of the talk. I gotta get some water. Oh, I didn't really talk about 1 either. That segment was really about E. I hope you noticed. E, 2E pi didn't make a really great title. I thought 1, 2, 3.14 had a bit better sound to it. So I hid E behind the number 1. But now I really am going to talk about the number 2. Okay, so this comes from my teaching, and it's to do with music. So there's a banjo, and actually it's this banjo. That banjo is this banjo, and it's also that banjo there. This banjo here, that's my dad playing with his dad. I come from a long line of banjo players. And it would be a better story, that's me with my dad. It would be a better story if I actually started playing the banjo around this time, or a little bit older. But I only started playing the banjo about 10 years ago. So, but anyway, that's the same banjo. Here, it's right here. My dad gave it to me eventually. And we're going to talk about a problem I thought of to do with banjos. I didn't think about this in connection with teaching, though. I used to stare at this banjo. My dad didn't have a case for it. I used to stare at it, leaning against the wall. He didn't even have a stand for it. And I always wondered about the pattern of the frets. So the frets are these little metal things that cut across the fingerboard. And if you've ever looked at one, a banjo or any fretted instrument, you see that the frets get closer and closer together as you go down the instrument. And as a kid, I used to wonder about that. Like, what's the pattern? Why does it do that? Why do they get closer together? And I also, as I got to be a little older, wondered, well, what if they just went forever? So, what if you just continued that pattern forever? If the frets continued forever. So I said what the frets are. Some people don't know what frets are. So anyone? I want you to understand me from here on out. So, any questions on what the frets are? Just those metal wires. There, you can see the frets there. Those little metal wires that cut across. They've marched down in a pattern down the neck. And the problem is, if the frets continue forever, the banjo would do what? Break into 1,000 pieces. So that's my joke, but I put that in there as sort of a break point because, of course, you can't really continue the frets down the neck. This is not a real problem that you could go and check. But it's still an interesting intellectual problem to imagine that the frets are infinitely thin. Because if the frets have any width at all, then they're eventually going to bump into each other, right? So that's the answer. They eventually bump into each other and you can't continue. But I'm imagining infinitely thin frets. Just no width at all. Just figure out the pattern, imagine they're infinitely thin, see what happens if you go forever. So here's some other possibilities. You continue it forever, okay, so that means you need an infinitely long neck to accommodate all those frets. Maybe that's it. Or maybe not. Maybe they call it a convergent series. Maybe it actually adds up to a finite number, but you'd need to extend the banjo. Or maybe nothing. The banjo, it just fits. So those are some, you can also think of some answers yourself. So I kind of wondered about that for a while, and then I was teaching this math and music class, so I decided to go ahead and answer the question. I didn't really know how to answer it. I need to find out some facts about the pattern. I actually didn't know what is the physics and the mathematics behind that. So I'm going to tell you that now. We'll answer this question. It's actually kind of a cool and not too complicated answer. So I want to just discuss a little bit about how banjos make sound and the lengths and the frequencies and things like that. So what I have marked on the banjo there is there's a hash mark right up there, and that's right up at the end of the banjo. That's called the nut. That's where the string is sort of tied off at that end. And then this hash mark here lines up exactly with the bridge. So there's a nut in the bridge, and that L1 is called the speaking length of the string. So you have the string, and it's tight there, and it's tight there, nut, bridge, and you pluck it, makes a sound. So it's vibrating, and it's tight there. So that the length that is vibrating is called the speaking length. And I've got that. I'm going to call that L1 for the whole rest of the talk. And then I'm going to talk about where you put the 12th fret. So, this notch here, if you follow it up, goes to this fret here, and if you count, it's the 12th fret. And I'm going to call that L2. And why the 12th fret? Why am I interested in the 12th fret? Well, you've probably all seen a piano before. And so there's a picture of a piano, the keys on a piano. And if you start anywhere on the piano, so I'm going to start right here, and start counting up on adjacent keys of the piano. You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You wind up there. And that is the white key right below the two black keys. And I started on the white key right below the two black keys. And it's called jumping an octave, and people perceive that as the same pitch. If you hear two octaves, notes an octave apart playing, you will perceive that as the same pitch. And the point is that there are 12 these are called half steps. Each of those little steps I took in music is called a half step, or a semitone, or a semitone. So 12 half steps, and you get back where you started in a note. So that's not true from just C to C. That's true start anywhere and count up 12 half steps, you'll be back where you started. Many of you know this, but many of you don't, so I have to bring everyone along here. So that's why I do the 12th fret, because on a banjo, the frets are actually placed to create these half steps. So when you go up 12 frets, you've gone up 12 half steps. So where that mark is at the 12th fret is exactly the octave point on the banjo, or any fretted instrument in Western tuning. I'll talk about other tunings a little bit later, but in Western tuning, 12 frets is 12 semitones, and we've jumped an octave. Now, just a little bit about the physics of sound, so I just want to tell you one physics law of how sound is created. And for that, you need to know that the string is vibrating, and you can keep track of how fast it's vibrating with a parameter. They call it the frequency. So the open string, L1, will be vibrating with some frequency. And just for an example, I'll say 440. Let's say it's vibrating at 440 little wiggles per second. They call that the note A. You've maybe heard of A440. So associated with a string vibrating, given length, is a frequency. And the frequency is perceived as a musical note. And that will be true for the other one, too. So I put a little wiggly shape there, and I have a second frequency that goes along with that length. And we wouldn't expect that this frequency is the same as that one up there, because that's the open string, and this is the fretted string. This is when we put our finger down right behind the 12th fret. So it turns out that the length and frequency are inversely proportional. That's expressed this way. Now, I know some people, including me sometimes, when I start to see so many variables, my eyes, especially this late into a talk, my eyes sort of roll up in my head, and I can't keep things straight. But this is L2 divided by L1 is equal to F1 divided by F2. And the loosey-goosey kind of feel-good way to explain that is the longer, or let's say the shorter the string, the higher the frequency. You shorten that string, you shorten the string from L1 down to L2, it speeds up the frequency. So if that one was vibrating at 440, like I said, this one would be a number higher than 440. It turns out it's 880, actually. But so L2 to L1 is F1 to F2. It's called, the quantities are inversely proportional to each other. So that's a physical law that governs music production. And it's true as long as you don't change the humidity and change the things like the temperature. And if you hold all the other variables constant, that will be the way those parameters behave. So now we're ready to solve the forever frets problem. And I told some people this summer that I teach this math and music class, and they said, "What do you do at the beginning of the class? How do you start the class? You hold up a triangle? Math and music, get it? Triangle." My wife told me that joke. She assured me that joke would go over well in the hands of Steve Martin. So thank you for your chuckles. So no, I'm not I want to get a little bit deeper than the triangle. The main thing that we need to bring to solve this problem is that when you double the frequency, that 440 number, or whatever is counting how many beats per second, you double that, it takes the pitch up one octave. So just as an example, if we were talking about A 440, take 440, double it, 880, that will be the A an octave above it. And if you double it again, that will be the A another octave above that. And if you cut it in half, that will be the A an octave below that. Why? Because when you double 220, you jump up an octave. So if that was an octave jump, then jumping down would also be an octave jump. So if you cut it again in half, 110, that's the A below that, and so on. 55 is another A. You could hear all those. You'd hear all those on a piano. So doubling frequency takes us up one octave. So here we're going to combine the facts. So there's this physical law of the inverse proportionality and the doubling fact about octaves. So there's the physical law, and that's in mathematics, now that's written as the doubling law. The new frequency for an octave, the new frequency will be twice the old one. So the 12th fret is an octave above, right? And I'm just going to use that law. L2 to L1 is F1 to F2, so I got most of it written there. But F2 is 2F1, so I'll put 2F1 down there. The F's cancel, you get a half. So L2 over L1 is a half, and you get that L2, solve that expression now for L2. The L1 pops upstairs, you get L2 is L1 over 2. So the 12th fret, fret 12, it's right right there. It's exactly halfway from the nut to the bridge. Exactly halfway. So I'm going to take you back to that picture, and this is indicating where the 12th fret's supposed to be, and it's half the length of that. So I'm going to move that half over there and ask you to rethink this thing. Think it through one more time. Pretend the nut is actually at the 12th fret, and see where the 24th fret should be. The 24th fret will be the next octave. A banjo doesn't have 24 frets, but it would be right about here, exactly halfway, another half, right? I don't need to do the calculations again. I'm using the same reasoning that I just did. And then the 36th fret will be another halfway like that. So it steps down in halves like that. That's the pattern. So 12th fret, halfway, 24th fret, which doesn't exist, another halfway like that. So there's the pattern. You see the pattern? It's always another half of the preceding. So I'm going to add these numbers up. And just bear with me, we're almost done. And this slide is a little bit busy. It took me a long time to get everything just right on this slide. But we're going to add those numbers. So the L1 over 2, then the L1 over 4, then the L1 over 8, and we're going to continue that forever. Okay? It turns out to be, it is a finite number. We factor out the L1. So all these terms over here, they have a common L1. So factor it out. There it is. And the numbers we're left with are 1/2, 1/4, 1/8, and so on. I'm going to call that bracketed expression S for sum. Okay? That's the sum. And I'm going to convince you now that this is a finite number, this sum. It's a sum of an infinite number of terms, but it's a finite number. So I've rewritten it there. S is 1/2 plus 1/4 plus 1/8 plus 1/16. Just rewriting that thing, the next term would have been 1/16, right? Goes forever. And here's a great trick. I wish I thought of this trick, but I don't know who did. Mathematicians use this trick all the time. When they see a pattern in the numbers like that, they come and they multiply the left-hand side by 1/2. So 1/2 S. You have to imagine now, bracket off this whole thing, that equation, S equals 1/2 plus 1/4 plus 1/8, and so on. Bracket it off, put a 1/2 in front of the whole thing. You get 1/2 S on the left-hand side. And what are you going to get on the right-hand side? Well, 1/2 is going to multiply by that 1/2, and it's going to give you 1/4, right? And then 1/2 is going to multiply by that 1/4, and it's going to give you an 1/8, because 1/2 times 1/4 is an 1/8. And 1/2 is going to, so on. 1/8 gets hit by a half, turns into a 16th. 1/16, and so on. It goes like that. The whole 1/2 of it just shifts the whole thing over like that. So now I know something about S, and I know something about 1/2 S. So I'm going to subtract S, knock off, subtract 1 half S. S minus half S. What do you get? Well, on the right-hand side, you get a half minus, I'm going to do it in columns here, a half minus nothing is a half, and then a quarter minus a quarter, 0, an eighth minus an eighth is 0, a 16th minus, you get zeros from then on, right? So this is a trick to add an infinite number of terms. So now I just simplify this arithmetic here. S minus a half S leaves me with 1 half S. So you got to be careful to see that this minus didn't just change to plus. It's just that S, take away half of it, leaves half of it. That's what happened there. And then we have a half plus a bunch of zeros is a half. So solve, that's an easy equation to solve for S, right? S divided by 2 is 1 half S. Multiply both sides by 2 and you get S equals 1. So that big bracketed thing, even though it looks ugly and infinite and everything, it's not. It's just 1. So I'm copying the last, or the top line there. I'm copying to the next slide, and I know that S is 1 now. And so if S is 1, then the whole thing, which is adding up all the fret distances, is exactly equal to L1. It's this L1 times 1. L1 times 1 is L1. So the octave frets, the 12th, 24th, 36, like that, you follow all those octave frets out forever, do it forever. It's exactly going to hit the bridge, because L1 was the distance from nut to bridge, right? So it exactly hits the bridge. But now I want to talk about different tunings. But I'm getting thirsty, so just a sec. Throughout music, not just in Western music, but throughout music in all over the world, an octave is an octave. So it doesn't matter how you divide the octave up. On a banjo, it's divided up, or a guitar or ukulele, it's divided up into 12 equal parts. But it doesn't actually matter how you divide it. You could divide it into 57 if you wanted to. But they would all be squeezed between those octave frets. So you'd have all the frets squeezed between the first octave, and then you come down half the distance. The frets, however you're dividing the octave, will be squeezed between those, then those, and those. So as you continue down, you get that all the frets continue forever, converge at the bridge. I focused on the octave because you can sum that series really easily, but it's not just, I didn't just deduce something about the octave frets. I got it so that all the frets on any fretted instrument in any tuning, and even in Western tuning, if you want to do equal tempered tuning or just tuning or anything in between, any types of tuning, any types of whatever throughout the world, if you have a fretted instrument and you continue the frets forever, it's a mental exercise, they would converge at the bridge. And it's not like carpentry where it works, it's within a 64th or so, that's good enough. This is perfect. It's a perfect fit. It exactly fits. I just think that's amazing. I don't know about you, but for me, that is a beautiful fact. And I think it's a good place to finish. I just want to tell you about one fretted instrument, okay? So that's my grandfather. That's another picture of my grandfather, who I did not know. His name was Swinburne Annandale Kayll. And there he is, dressed to go to a costume party. He's not Russian. He's Scottish. And he's holding that instrument. It's called a balalaika, and it's this balalaika. And that picture was taken around 1920. And my parents gave me that balalaika last summer. And I don't know how to play the balalaika. But I think it would be fitting to end this talk with a little music. So I got to conquer my nerves and play a little tune on this bell. This balalaika is well over 100 years old. Okay, are we mic? Can you hear me? thank you very much for your attention. What's that? Oh, the drawing. Right, the drawing. I've been reminded about the drawing. Yes. So I'd like to, first of all, thank my assistants, my trusty assistants who gathered these. I'm not going to name them all because there's about 10 of them, and I don't know all their last names. So anyway, thank you. I'll see you in class. I do have a special, I call her my lovely assistant. So will my lovely assistant please come on stage, and we're going to draw. First correct answer gets a pie. The pie that my daughter helped me make. Okay, so here it is. That's the pie. Same pie. It's carefully wrapped. And go ahead. Anastasia Halfpap is in my 400 level graph theory class, and she's also the daughter of one of my colleagues, my trusty assistant. The answer is...
This one is?
Okay. Christopher B. Are you still here? Christopher B. gets a pie on the first try. Come on up. Thank you, Anna. It's a plum pie made with plums from my neighbor's tree.